Welcome, focused learners, to the Explainer. Today we are putting on our flight suits, jumping straight into the cockpit, and adopting what I absolutely love to call the Top Gun mindset for tackling the Cambridge Computer Science syllabus. Look, whether you are studying syllabus 0478, 0417, 2210, or even pushing into A-level 9618, you already know that flying at maximum altitude requires advanced aerial combat tactics. You can't just know the basic parts of your aircraft, you need to know exactly how to maneuver it under intense ticking clock pressure. And in this explainer, we're decoding the ultimate exam strategy for one of the most notoriously misunderstood topics out there, binary addition and overflow. We're going to look closely at real past paper questions, break down exactly what the examiner is secretly begging for, and build an airtight system that guarantees maximum marks. Okay, let's dive right into this, because honestly, this is the million-dollar question. You've studied the textbook, you know how to add ones and zeros in your sleep, so why do students who know their binary definitions inside out still lose vital marks on exam day? Imagine a real Cambridge past paper question sitting right in front of you. Explain the effect of an overflow error in an 8-bit system for 4 marks. Let me introduce you to 2 classic student archetypes. We've all been one of these at some point. First up, we have Alex. Alex is the overloader. Alex stuffs answers with raw computer science facts, totally ignoring any real analysis. Alex writes, binary addition is 1 plus 1 equals 10. Overflow is when the number is too big, the maximum 8-bit number is 255. On the other side of the exam hall, we have Sam. Sam is rushing. Sam completely misses the command word requirements and just writes, it overflows and crashes the computer. Now, both of these students have pieces of the truth, right? But if we overlay the examiner's red pen, Alex scores maybe 1 single mark for mentioning the maximum number, and Sam scores a flat 0. They both literally crashed before they even left the runway. Why? Because they lacked a structured step-by-step strategy.
To fix this, we need a solid flight plan. Here is our blueprint for today. We're covering the binary exam trap, the 3 layers of explanation, the method mark strategy, the importance of context, avoiding mistakes, and finally, your final self-check. Let's get into it.
Starting with Section 1, the binary exam trap.
So, the huge problem with binary addition and overflow is that it's almost always taught and learned as this isolated mathematical trick. You memorize the rules. 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 0, carry 1. Simple, right? But here is the trap. Those surface features totally distract you from the real mechanism. An exam question isn't just checking if you can do primary school arithmetic, it's actively assessing your deeper understanding of how physical hardware limitations impact digital systems. This brings us to a massively vital distinction you need to lock in. Notice the stark difference between description and explanation. A description merely tells the examiner what the process is. For example, overflow is when a calculation produces a result greater than the CPU register can hold. Okay, that's a safe, accurate, but incredibly shallow description. Explanation, on the other hand, tells the examiner exactly how it works and why it actually matters. A top-tier explanation sounds like this. When 2 8-bit binary numbers are added and generate a 9th bit, the CPU register, which only has 8 physical storage spaces, cannot store this extra bit. This results in an overflow error, causing the system to either drop the most significant bit, leading to wildly inaccurate data, or flag an error that could crash the program. Do you see the difference there? It's huge. Examiners expect both. If you only describe, you immediately lose half the marks. If you jump into explaining without naming the process, your answer sounds confused. You absolutely need to marry the two together.
And that marriage is achieved through what we call real-world transfer. Basically, this means taking a memorized abstract concept and converting it into a useful, context-driven solution. A strong exam response always begins with a digital problem and links directly to the practical consequences for a user, a system, or an organization. This is exactly where top students use the PEAL framework. Have you heard of this? Point, evidence, explanation, link. It is a game changer. You make your point, a 9th bit is generated. You provide evidence from the scenario. The register is only an 8-bit register. You give an explanation of the mechanism. The bit physically cannot be stored. And then crucially, you link it back to the real-world consequence. The automated system calculates the wrong coordinates and crashes. That framework is exactly how you secure top marks without breaking a sweat.
Moving into Section 2, the 3 layers of explanation.
Now, what's really interesting about this slide is how it bridges the gap. Because listen, if you want to perform under the high pressure of a timed Cambridge exam, you cannot just rely on your initial basic understanding. You have to build your knowledge in distinct layers. Layered learning bridges that massive gap between simply nodding your head in class and writing a perfect answer when that exam clock is brutally ticking down.
Let's break down the cognitive process of a top-tier student. Step 1 is everyday language. This is where you understand the concept like you're explaining it to a friend at lunch. Overflow is like trying to pour a liter of water into a half-liter cup. It spills over and makes a mess. That's fantastic for conceptual grounding, but honestly, it scores 0 marks. Step 2 is technical vocabulary. Here, you upgrade your terminology. You upgrade the water cup to a CPU register. You upgrade the water to binary bits. An overflow error happens when a binary value exceeds the maximum capacity of the allocated storage. It's definitely better, but still not quite at the finish line. Step 3 is the exam-level explanation. This is where the magic happens. You shape those ideas into a time-pressured, mark-yielding response. You combine the technical vocabulary with the specific command words of the question. You explicitly mention the 8-bit limit, the generation of the 9th carry bit, the loss of data integrity, and the resulting system state. Shaping everyday ideas into these structured responses is exactly how you secure maximum marks.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's jump into Section 3, the method mark strategy.
Look, instead of treating your exam page like a blank canvas where you just randomly paint whatever facts you happen to remember, I want you to treat your exam technique as a strict, logical, step-by-step algorithm. If your exam answer is out of sequence, the marks simply won't register. Here's your disciplined 4-step computer science success blueprint. Step 1, identify demand. What is the actual command word? Is it state, describe, explain, or evaluate? If the question says explain, you cannot just list facts. You must provide reasons and mechanisms. Step 2, classify concept. Recognize that this isn't just a math question. Oh no, it's a hardware limitation question regarding memory size and data integrity. Step 3, explain sequence. Process-based topics require a logical flow. Do not jump backwards and forwards. You start with the calculation, move to the generation of the extra bit, explain the physical register limitation, and end with the error flag. Step 4, connect to context. Apply this sequence to the scenario given in the question. Sequential, structured reasoning produces clear answers that examiners absolutely love to read. It takes all the guesswork out of grading. Think back to Alex and Sam from our introduction. If they had used this 4-step algorithm, Alex wouldn't have just dumped random facts, and Sam wouldn't have skipped the mechanism. They would have hit the target dead center.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Awesome. Let's pivot to Section 4. Context is everything.
As we look at specific situational context, you need to realize that this is often where the absolute highest grade boundaries are decided. The difference between an A and an A star often lies purely in how well a student anchors their technical knowledge to the specific scenario provided in the exam paper. You don't just have to take my word for it. Here is an authoritative quote directly from the Principal Examiner Warnings: generic responses rarely gain full marks. So the crucial point is this: you can write a perfectly accurate, beautiful technical explanation of an overflow error, but if the question asked about a factory control system and you never once mention the factory, the machinery, or the sensors, you are literally leaving marks on the table. You are answering a question that wasn't asked.
Consider how familiar technologies work, like our phones, websites, databases, automated systems, robotics, or secure online banking. The exact same patterns of binary addition and overflow appear in all of these. Let's do a quick mental workshop. Imagine you have 60 seconds on the clock. If I tell you an overflow error occurs in an automated robotic system, your context connection should be lightning fast. The robotic arm calculates a movement coordinate that exceeds 8 bits, causing an overflow, resulting in the arm dropping its positional data and potentially crashing into the assembly line. What if the context is secure online banking? Your connection shifts entirely. A financial transaction calculation exceeds the maximum integer limit of the database field, causing an overflow that wraps around to a negative number, resulting in a completely incorrect account balance. The core mechanism, that pesky 9th bit, is identical. But the application proves to the examiner that your knowledge isn't just floating in abstraction. Your answers absolutely must stay inside the given scenario.
Let's transition into Section 5, avoiding common mistakes.
Look, understanding how to do it right is really only half the battle. Knowing exactly where students bleed marks on the page is what gives you the ultimate edge. Let's do a rapid-fire find the flaw session with these examiner-identified pitfalls. First up, using vague wording.
saying things like, the computer gets confused. No, computers don't have feelings. Instead say, the CPU generates an overflow flag. Second, confusing similar terms. Mixing up memory with storage or confusing an overflow error with a syntax error. They are completely different concepts, and examiners will penalize you for swapping them. Third, missing steps in a process. In process-based topics like binary addition, jumping backwards and forwards breaks the logical flow. You literally can't talk about the system crashing before you explain that a 9th bit was generated from the addition of two 8-bit registers. Fourth, ignoring the given context. We just hammered this point home. Don't write about generic desktop computers when the question is specifically about a washing machine microcontroller. Fifth, stating an advantage without a reason. If you write detecting overflow is an advantage, you must explain why, because it prevents corrupted data from being processed further. If you can spot these flaws in your own writing during your mock exams, you will instantly elevate your entire grade profile.
Finally, we reach Section 6, the final self-check. We've decoded the command words and applied the frameworks. Now, here's the ultimate verification mechanism. These are the 4 critical questions you must ask yourself to verify your knowledge before moving on to the next page. Number 1, what is it? That is your core concept, your basic definition. Number 2, how does it work? That is your mechanism and sequence, the actual step-by-step logic. Number 3, where is it used? That is your context and scenario, the real-world application. Number 4, why is it better or worse? That is your justification and evaluation. Listen, if you can look at an exam topic like binary addition and overflow and verbally answer these 4 prompts aloud in your room without checking your notes, then that topic is fully locked in. It is officially ready for the exam hall. If you stumble on even one of these questions, you need to scratch that, circle back, and run through another revision cycle. This matrix is your guarantee. It forces you to cover all assessment objectives comprehensively.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.